All right, thanks everybody. Welcome to our third edition of the ASPEN Net Quantum Networking Tutorial Series. And today we have a double feature for you, so to speak. So we've got two talks. The first will be given by Marty Stevens from NIST and the second by Paul Kwiat. I've known both of these folks for a very long time. Marty Stevens, I uh, started working with when I was in grad school. He was working here at NIST and worked with him for, I joined NIST and I've worked with him for the past 11, 12 plus years. And now Marty actually leads the group that I'm a part of here. So Marty's a world expert on detector technology, specifically the superconducting nanowires. Our second talk will feature Paul Kwiat from the University of Illinois, Urbana-Champaign. And Paul, I've also known for a very long time, actually also when I was in grad school, and know him through both a swing dance connection and through a quantum physics connection, and have had the pleasure of collaborating with them. And he's actually my kind of my uncle, so to speak, academically. So yeah, there's a known both these folks for a long period of time, and I'm really excited to hear what they talk about today. So we're going to hand it over to Marty, and we'll start with our detector work.
Great. Thanks, Krister. It's a pleasure to be here this morning. So before I talk about detectors per se, get on here. I got to get back to where I can advance my slides. There we go. I want to give a little bit of a setup, and hopefully some of this is review from the last time. I think Mike Mazurek covered much of this about the basic idea of this path entangled network. So one of the first building blocks of this is to use spontaneous parametric down conversion, or SPDC, to generate heralded single photons. So the simple idea is that there's a pump beam that comes in. There's some high energy pump beam, and it has some nonlinear medium here with probability of generating 2 photons. And if one of those photons goes over here to a detector and gets detected, then we herald the presence of a photon in the other mode. So often we talk about these things in nonlinear optics as a signal in an idler beam, and in that language, you can think about the state generated here coming out of the crystal, approximately speaking, as something like some probability of getting 0 photons in both modes, some probability of getting 1 photon in both modes, and some probability of getting 2 or even higher order photon modes. And it turns out that if you look a little bit carefully here, the probability of getting 2 photons goes roughly as the probability of 1 photon squared. So that tells us that if we operate in very low limits, very low rates, it's easy to only get 1 photon over here in the signal mode. But the problem is we're going to often also get 0. So that's not an ideal place to be. So what we'd really like to be able to do is herald these things so that run it at a higher rate, and then find out when there are 2 photons present, be able to actually tell the difference there. So these heralded, the idea for this all photonic path entanglement swapping scheme is essentially to have two of these sources. There's one heralded single photon over here, one heralded single photon over here, and these would generally be in remote locations. Each of those photons goes off a beam splitter and then is in a path entangled state. So essentially, the photon is in this superposition of having transmitted through the beam splitter and also been reflected by the beam splitter. We can write that as this superposition state over here, and as also as a superposition state over here. Now, if those photons are allowed to travel from the 2 remote stations towards this center station here, where there's an entanglement swap can happen, if those 2 photons are identical to one another, so they've got the same polarization, spectral, temporal profile, all of that, they arrive at the same time, then if one of these detectors clicks, and only one clicks, that heralds the presence of an entangled state, basically entanglement between this path over here and this path over here. So now we've generated we've heralded the presence of this state, and it's basically 1 photon over here on the left in Alice's lab, with 0 photons in Bob's lab, or 0 photons in Alice, 1 photon in Bob. But you can also see there's this e to the I phi term here. This, of course, requires this phase stabilization across the entire network. That's a very difficult part of all this, but I'm really not going to talk at all about that today. What I really want to just talk about is the single photon detectors that are required for this scheme. So there are 2 types of detectors that are, broadly speaking, that are needed here. There are heralding detectors, and you see in this simple version of this, there are 4 detectors required. So 1 at each source and two at the swapping station here. And a different type of detector here is the measurement detector here. So what happens, what I didn't mention is that in order to do the measurement to verify this entanglement, what we have to do is basically take a local oscillator, a very weak coherent state, over here at this measurement station, and interfere it on a beam splitter with the photon that's coming here off this beam, this first beam splitter. So, and we do the same thing over on this side. So these measurement detectors require slightly different characteristics. They have to optimize in slightly different ways. These are all single photon detectors, so they must be single photon sensitive, but we have a little bit different requirements, and I want to talk about the specifics of what are required from those detectors. So here is a slide with kind of a basic outline of our target for sort of 1 year from now, what we need to be in terms of detectors to make the first interesting measurements in interesting demonstrations. So I'm going to show these radar plots, and I'll show several of these. So let me just kind of walk through what we got. So we got 4 different axes here. We've got number resolution going out to the left, 1, 2, 3, 4, 5. We've got efficiency here going up, and you can see that we've really zoomed in on very high efficiency. Anything below 90% is not terribly interesting to us. So there's a lot of detail and just how close to 100% you can get. Off to the right, we've got count rates. This is a logarithmic scale. There's quite variety there. And then down below is timing jitter. So on each axis, the common theme is that the farther away you are from the origin, the higher performing that detector is, and probably the more difficult it is to actually make that thing work. And there are some trade-offs really between some of these axes. There have been demonstrations way out at the edges of all of these corners in individual detectors, but no one detector has filled this entire area here. And that's an ongoing challenge. So for the measurement detectors in that kind of first year, we really need very high efficiency. I mean, the measurement detectors in general, we need extremely high efficiency. We don't really need number resolution in either detector right away. Some fairly modest timing jitter and some fairly modest rate. And I'll show that we have state-of-the-art detectors that are quite close to this already. For the heralding detectors, we can get by with sort of lower efficiencies to start here, somewhat lower rates. So this is actually for the initial demonstrations. We believe we can do this either with existing detectors or just slight tweaks to detectors we already have. If we look a little farther down the road, sort of 3 to 5 years, you can see that our requirements are going to get more strict. And in particular, on the measurements, both measurement and heralding side of detectors, we're going to want to operate at much higher rates. Now, these rates are not especially high given for sort of state-of-the-art nanowire detectors, but they are very high for nanowire detectors that have this incredibly high efficiency, 98 to 99%. And then the other thing you'll notice over here is on the heralding side, we're going to require some number resolution. That goes back to what I was talking about early on introducing down conversion, is that, we want to know when we're generating, we want to be able to make sure that we sent one and only one photon into that heralded mode and out into our experiment. So we've really got to be able to identify when the source emits 2 photons, we've got to catch that. And you've got to really have very high efficiency, because you can imagine, even if you say, well, I have a detector that can tell the difference between 2 and 1 photons, it's only really useful if you have very high efficiencies. Because if you think about it, you have low efficiency, let's say a 50% efficient detector, and you're trying to identify a 2-photon event, well, half of the time you're going to misidentify a 2-photon event essentially as a 1-photon event in that case. So it's really not terribly useful. So you really need very high efficiencies for that. And then looking even farther down the road, things are going to have to fill out even more. But in terms of number resolution, we don't really anticipate we need a ton of number resolution. We really need to tell the difference between 0, 1, and 2 or more. Anytime there's 2 or more photons in that heralded mode, we just ignore those photons. But you can see the requirements on the rates is going to get much more stringent, and the requirements on the timing jitter, and then of course the efficiency requirements are going to just keep creeping up. It hasn't moved a lot on here, but I can assure you that that last 1 or 2% getting towards 100% is, of course, extremely difficult. Okay, so the way we're doing this is superconducting nanowire single photon detectors. These detectors have been around about 25 years now. And we've been working on them here at NIST for most of that time. The basic idea is you've got a very thin, few nanometer thick wire, maybe hundreds of nanometers to microns wide, and we can run, and it's superconducting. So we hold it at a very low temperature, and then we run a bias current through this thing. And the superconducting wires have a critical current in which if you exceed that critical current, it's no longer superconducting. It's just like a critical temperature. If you exceed critical temperature, it turns into a normal resistive metal. So,
Hey, Marty.
yes.
So we had a first question in the chat from Duncan England, who said, I really like the radar plot as a way for visualizing detector performance. A fifth axis could be dark counts. Could you comment on the dark count requirements?
Yes, I agree. A fifth axis would be, and we've made sort of 5 or 6 axis versions of these things. I think dark counts, we tend to feel that's a pretty solved problem, that we can do very low dark count rates. In fact, with the nanowire detectors, it's routine that you have sort of 100 counts per second. They're actually not true dark counts. They're actually really mostly it's black body radiation from room temperature that gets into your experiment. But with proper filtering, it's not so bad. And the thing is, those dark counts tend to be dispersed evenly in time. So if we have very low timing jitter detectors, we know exactly when to look for our signal in time, and then we can ignore all those other things. But it's certainly something we need to keep an eye on. So the basic way that we run these things is we hook up a nanowire to a current source. We set the bias current really close to this critical, so the whole wire is near this critical current density, and then we wait for a photon. And when a photon comes, it's going to generate a hot spot. That's a resistive region, and we're going to get a voltage pulse out. So the kind of roughly speaking equivalent circuit looks something like this. So here's a pretty small version of a nanowire, but you can see rather than having one single wire, which is going to be very hard to couple light to efficiently, we tend to have a meander where the wire, meanders back and forth across some larger area here. And then it makes it easier to couple our photon to. So that's basically equivalent to some inductor in series with a variable resistor. And then when we apply a bias current to this, there's no voltage out of this thing because the resistance of the nanowire is 0. When a photon comes in, it's going to generate a hot spot here when it gets absorbed, and that's going to lead to some finite resistance on the order of a kiloohm or so. And then we can get some voltage pulse that comes out of there, which is on the order of, say, hundreds of microvolts, maybe millivolt level, which is really too small to see on its own, but we can use some fairly simple, inexpensive room temperature electronics to read that thing out. So here's a kind of typical readout configuration. Again, down in our cryostat, held at a temperature of around 1 Kelvin, maybe up to 4 Kelvin temperature. We've got our nanowire sitting there. We've got a bias current that comes down to it. And then we've got a coax line here for a readout, amplifier, and in this case, we can go to scope or time tagger or whatever it is we need to see. So here's a typical voltage pulse out, of amplified voltage pulse out in response to one single photon being detected. So you can see these very fast rise time on the order of sort of 100 picoseconds is quite typical. amplitude, well above the noise level here. It's quite easy to distinguish this thing from just background noise. Pulse duration tends to be a few nanoseconds, maybe tens of nanoseconds, sometimes longer, hundreds of nanoseconds. And then the large inductance of this allows the thing to cool down, reset, and be ready to absorb another photon. So that's the kind of basic operating principle. That's all I want to go into there. Now I want to walk through where are we at in terms of state-of-the-art detectors. Well, this is a result out of our group at NIST here from now 4 or 5 years ago. Just realizing I put the wrong year on my slides down here. We're still living in the past. So this was a very nice result. Varun Verma, Dilip Reddy made this device and tested it. And the basic idea is, here I'm showing on the right the way we achieve really high efficiency, and that is to embed the superconducting wires into a dielectric stack. And essentially the idea is photons here coming down from the top. There is this superconducting layer here, this meander of wires, and then there's this Bragg mirrors basically above and below the detector, essentially like an anti-reflective coating here and like a mirror down below, and then it's finely tuned to get really high efficiencies. So Dilip demonstrated these devices with 98% efficiency, and it wasn't just one hero device. There's actually, in the paper shows, the first 4 devices he tested out of this wafer were very much same efficiency. One of the ways that this high efficiency was achieved was by scaling these to large areas. And so this shows the active area of the device. And you can see that it's going to make it easier. So the way the detectors work, I didn't mention, but we have a single mode fiber that couples down into the cryostat to the detector. So the mode field diameter out of that fiber at 1550 nanometers is around 10 microns. So scaling up to 20, 30, even 50 microns makes it even more likely, even with slight misalignment, that you catch all those photons. This is actually an area of pretty active debate in our group at the moment, whether we really need to. We don't actually think we need to scale to such large sizes. But what you can see here is that the larger size, the voltage pulses that come out are just longer. They take longer to recover. And you can see here, zoomed out over really long time scales, even after 20 microseconds, this detector is not ready again. So at this is like, what is this, 500 kilohertz or something like that count rate. So it's really not going to be great for very high speed operation. So let's see how these detectors stack up to our requirements. This is I'll compare it just to the measurement detector, because that's where this detector is most likely to be useful. Our kind of 1 year goal, you can see the efficiency were there. Number resolution were fine. The rates may be a little low. These particular detectors had quite low jitter. But we think with slightly different versions that have a smaller meander, that we can get back to this same high efficiency and also match the rate and jitter. And of course, when we look 3 to 5 years in the future, we're going to need to bump that efficiency up even a little higher, and then really make substantial progress on rates and timing jitter. Skip that. Well, I guess I can say for the heralding detectors, you can see, well, maybe you can see that efficiency, we're there, but number resolution on these particular detectors is not likely to be there. So let me talk a bit about number resolution with nanowire detectors, because this is an area that has really taken off a lot in sort of the last 5 years or so. That there's not really an intrinsic. They haven't been early on when they were used. They were just seen as a click detector. Either you have 0 photons recorded or 1 photon recorded. But here's a figure from a recent paper just showing kind of principle of operation. So here's this cartoon of the nanowire. You can think about if you have 2 photons that come in and they generate like a single hot spot, or if you have high energy photons, this is the voltage pulse as a function of time. And what you see is as the number of photons in that hot spot increases, you shift over, and earlier and earlier times that voltage pulse arrives. Or even if those photons don't end up in the same area, but they end up in different areas of the different domains, you can still see a change, not in the arrival time, but in the slope on that arrival. So really looking carefully at the the incoming slope and thresholding carefully, folks have had quite good success with number resolution. Here's some nice work out of Tim Bartley's group from last year over in Paderborn University. And what you see is here's the voltage pulse coming out of the detector as a function of time. And then here is a zoom in on that very steep rising edge. And what you actually see is there are kind of a series of different curves that appear for 1 photon, 2, 3, 4, et cetera. And then when they take a histogram, essentially, they do a little bit of complicated analysis on this, but the histogram looks something like this, that they're able to see 1 photon events here, sort of at a later time, effectively. And then 2 photon events, they come a little earlier than 1 photon. 3 come in a little earlier yet, 4, 5, 6. So you see there's a lot of blurring here. You can't distinguish between 4, 5, and 6 with high fidelity. But there's this very nice gap between the 1 and 2 photons. So you can very nicely draw sort of a threshold in here. And you know that if your arrival time is in this range, that's a 1 photon event. And if it came earlier, that's a 2 or more photon event. We can throw those out. These detectors were not terribly high. I mean, they're high efficiency, but it's not sort of state of the art. They were done with just a commercial device that they happen to get from a company. And then the laser rep rate, I'll point out, is quite low here. It's like 100 kilohertz. So one thing you notice is that actually to achieve really good timing resolution, you actually want to slow things down. And so you'd like this rising edge to be even a little slower, and that as a result, you often end up with a very long recovery time. And you can see it's not as long as the ones I showed from our group earlier, but it's still, tens of nanoseconds. And you really want this thing to completely recover with no memory of the previous event before this next pulse comes in. And they found that really having to go to very low rates was necessary to do this. So that's something that's going to need to be better. Here's another recent paper showing this, the kind of, single photon and multi-photon. Again, there's not good fidelity between 2, 3, 4, et cetera, but multi-photon is very well distinguishable from single photon. And they were able to drive it at much higher rates here. And then a very recent paper on the archive, again, from the Bartley group. What you see here is a log scale histogram. There's a lot going on here as a function of time delay. But what I'll just point out is that this here seems to be the 1 photon peak. And then here's the 2 and more photon peaks over here. And one of the impressive things about this was it's a pretty high efficiency, like 91% efficiency. So, and I'll just remind you, this is a log scale. So you can draw a line here, very nicely distinguish 1 from multi-photon events. So let's see how this one stacks up to our requirements. The 1 year targets, we're pretty close. That's pretty close on efficiency. Certainly jitter and number resolution even exceeds what we have now. But as I pointed out, the rates of these kinds of schemes right now are actually still pretty low. And in 3 to 5 years, it's going to really need to be scaled up, higher efficiency, higher rates.
Marty,
yes.
we had a question in the chat I just want to
Sure.
ask. So it says, thanks a lot for the nice explanation. Can I ask why the thickness of the superconducting film is only a few nanometers instead of a few hundreds of nanometers?
Yeah, it's basically because if you have what we need is to destroy superconductivity across that entire cross-sectional area of the wire. And so, as I said, what we do is the way we tend to do it, the way the growth and fabrication of the devices works best, we can deposit a thin layer, a few nanometers thick, and then pattern it into, say, 100 nanometers wide or even a micron wide. We could, in principle, you could invert that and say, make it, a few nanometers wide by 100 or 200 nanometers tall. But that's going to be a very delicate structure, and it's just not something that we can fabricate very well. So it's really a matter of getting the cross-sectional area just right. There's also some underlying physics that are still not completely understood that we're actually exploring some of those things right now. But The basic thing is we make them that way because that's the way that we can make them, and that's the way we've shown we can make good devices.
Mike Raymer also has a question. Mike, I might just
Yeah.
have you unmute to ask, if that's okay.
Oh, yeah, sure. Hi, Marty. Are those test experiments done with pulsed sources? And if so, what are the pulse durations?
Yeah, so these number resolving are all pulse sources. Pulse durations tend to be kind of picosecond, few picoseconds or something at the most, because it's what it really requires. You need very low timing jitter in your entire system. So you need a low jitter detector, a low optical jitter source. So
Right. So if you had nanosecond pulses, if your single photons were nanoseconds in duration, you could not do this.
that's right. Yeah,
Okay.
not with this particular scheme anyway. Okay, so let me just try to briefly wrap up at the finish. There are some demonstrations of really high count rates. You see measured count rate. This is a device from the Matt Shaw's group at JPL. This device is called the Peacock. There's a bunch of letters that stand for things. I don't remember what they are, but you can see the device itself sort of looks like the fan tail of a peacock. And what it essentially is there's a whole bunch of wires meandering over the same area, and you can kind of multiplex to get even higher rates. And so you can see count rates, up approaching the gigahertz here. Let's see how that is comparing with what we need. The rates are really way off to the right here. The timing jitter is quite good. But the efficiency is, I mean, it's good. It's, what number do I have here? 78%, but it's certainly not the sort of state of the art. I've only run number resolution of 1 here, but actually, if you think about having enough of those wires, you get pretty good you don't get intrinsic number resolution. So, but you do get a pretty sort of crude number resolution. Okay, so just quick summary. Our detector challenge is really state of the art in multiple metrics. There are often these trade-offs: efficiency versus count rate, number resolution versus count rate. Good jitter is required for good number resolution. So both of those generally come together. But as I said, they can often be at the expense of count rate. And then I haven't talked about it all, but we have ideas for new designs, active reset. We really think there is a way to get all of these things at once. So that I'll take any more questions.
Feel free to unmute yourself if you have a question. We have time for maybe one more question, maybe 2.
Maybe I could just ask a quick one. On the detector side of things, we've been developing a multi-pixel approach.
Mm-hmm.
And there we get, well, it's 28 pixels. We can get your very good distinction between, well, most of those, but certainly 1 and 2. 90% efficiency, tens megahertz count rates, and the jitter doesn't go above 60% in that regime. It seems like promising.
I do. Yeah, that was an oversight on well, that was a matter of not having enough time on my part to get your stuff in here, but I should have
No,
asked
I
you for the
wasn't sure whether
slide.
it was that or whether you just fallen off the radar.
No.
It's fairly recent, so.
Yeah, no, I agree. That's doing these kind of multi-element designs is certainly, I think, a nice approach to doing this. And as you say, if you have a lot of elements, then it's not very often. What the concern is that 2 photons get absorbed on 1 wire and you miss those. But if you have enough of elements, that you don't miss very many.
Yeah, I think 28's plenty for doing one or more
Yes.
than one, so we don't get much of a loss there. So
What is the effective loss for that, Rob? Like 3-ish%, 5%, 2%?
well, I mean, like they're interweaved, so every pixel has the same probability of seeing a photon. So it's just your 1 over the number of pixels you got. That's your drop in efficiency. So because it's just the probability that wire is not active anymore.
That's about 3%-ish then.
Yes, I mean, yeah, you could put more in
Okay,
there, but yeah.
that sounds pretty good. Um, Okay, well, I think thanks, Rob. Thanks everyone for the questions, and thanks, Marty, for that
Yeah, my
short
pleasure.
but powerful tutorial. And we're gonna pass it over to Paul now, we're gonna switch gears and talk about quantum memories. So, Paul, yeah, feel free to share.
I'm doing it. Give me a new choice I've never been offered before. Continue to share using SharePlay or fine. Okay, that's fine. I think you guys can hopefully see normal slides. Oh, actually, I have this open on my other computer, so I can
That's
see.
good.
Good. We're all seeing what I think we should be. Okay, yeah. So thanks for the opportunity to come and just try and talk a little bit. One of the other key elements of this type of architecture. I've changed my title just a little bit as I always do, assuming this works. Okay, so little song reference here or something like that. So I can basically not spend much time on the ASPEN Net architectures other than to indicate where we need the memories, and then I will talk a little bit about competing ways of achieving what we need to do, and then kind of this free space approach that we've been following and how that's been working. And if there's time, just a quick demonstration of something that we've done that's kind of related to what we need to do here anyway, to show that the basic principle seems pretty sound. Okay, so Marty already went through these, so I don't need to, I'm not going to go through these other than to say, okay, well, we're trying to distribute by sending single photons and post-selecting or waiting until we get a click, for example, that prepares this mode entangled state. And have to keep track of the phases in order for that to work. Now, if we want to do this in an actual architecture, we need to take into account the fact that, first of all, a lot of the pulses that we send, because we don't have true single photon sources, if we're doing things with down conversion, and we don't want to have lots of multiple pair events. We can certainly detect some of them if we have photon number resolving detectors, but oftentimes we'll run these sources where every pulse has, let's say, 1/10% chance of having a pair in it. So that means that the pairs that are coming down the fiber to the central location system, I should say the time bins that are going down, many of them will be empty. Let's say 9 out of 10 of them will be empty. And if I sort of just do the things independently with the two sources, that's not great. I mean, that's empty even before we go through what might be a lossy fiber, which of course will remove more of the photons. So what I'd like to do is basically use heralding in order to determine, okay, which of the bins are empty and which are not empty, and then use memories so that the things that I finally try to interfere on this beam splitter are time bins that definitely at one point had a photon in them. Maybe they don't after this long fiber. And if any one of us comes up with a quantum non-demolition type of measurement that we can do on that, that might be very helpful. But in any event, yeah, we want to be able to synchronize the photons at this final beam splitter, and one can go to higher and higher occasions of this. So these are images I took from Mike Mazurek's talk. I guess it was 2 weeks ago. Okay, so you can go back and watch that to find out how that's going to go. Now, if we think about the way we want to do this, because a lot of the pulses are going to be empty, and of course we want to generate as much entanglement at the end as possible. Also, some of these, like Bell state measurements, only work 50% of the time. So we would really like to be sending photons as fast as we can, at as high a rate as we can. And the thing that's eventually going to limit that is going to be the detector jitter. So, if we have detectors that have a jitter of, 10 picoseconds eventually, then we'd love to be operating at 100 gigahertz, where we're attempting once every 10 picoseconds. And eventually, to get the rates even higher, one might want to have even multiple spectral channels, say up to 100 spectral multiplexing, which means then we need to be able to handle something like tens of terahertz in the quantum memories to be able to handle that. Or effectively that by doing some sort of a split into narrower frequency channels and then have a bunch of different memories and then re-adding things back together. All of that adds, again, a lot of complexity. Okay, so I'm not going to spend a lot of time talking about matter-based quantum memories, just so that we're on the same page of kind of how typically these are working. So typically, we have some sort of an atom or a solid state system. That's kind of the most common scheme, and we'll transfer the state of the photon into the state of the atom or into the state of the solid state system. And as indicated here, I mean, I'll go into detail in just a second, a little bit of detail, but the issue is that often these can have quite expensive overheads in terms of needing lots of laser systems, maybe cryogenic systems if we're talking about rare earth ions, something like that. And they'll also tend to be pretty narrow bandwidth. So let's just talk about that. So, one way that we might do this is with an atomic ensemble, where we have a three-level system, so-called lambda system, and our single photon comes in resonant with one of the two levels, and we can then basically, if one of the atoms is excited into the 2 state, we will drive it down, transfer it into the stable number 3 state. That's basically the memory state. And if we do this with an ensemble, if it's only one photon coming in, then only one of the atoms in this whole ensemble will be excited, but we don't really know which one. So we have this superposition, and then when we send in our control pulse, it basically undoes that superposition because all the relative phases between all the different atoms where they have all been maintained, and then we can get the photon to be spit back out after some time. Okay, and the way that this is often done is driving these things on resonance, and these resonance line widths can be quite narrow. So one might be looking at something that's like 100 megahertz or 10 megahertz. It's also possible to drive these off resonance, far off resonance. And when you do that, then you can have a substantially larger bandwidth. And so this is just this is a summary of a lot of different atomic ensemble-based quantum memories. This is from a paper by Gina Lorenz's group, Kai Shinbro there. Kind of comparing all of these different schemes, which again, this could be another 5 hours of talks on all of these. This is their off resonance work, which, as you can see, has a quite high efficiency and also relatively high bandwidth, up to 1 terahertz. Certainly much higher than most of these other schemes are. But in that case, the memory lifetime is not super high, so only something like a nanosecond. Okay, but I will say that. So let's just talk a little bit about lifetime. We don't necessarily need lifetimes of many milliseconds or seconds or something like that for what we're trying to do, because we're just trying to do this synchronization task. And that might require us to synchronize, let's say, 100 pulses. And if they're coming, let me just say every nanosecond to make the math easy, then we only need to be able to store for something like 100 nanoseconds in order to be able to do this synchronization. So a little bit different than other examples where we might need a much longer memory lifetime. Here we can get away with something quite a bit shorter. So you might say, well, okay, do I just go through a fiber? Certainly if I go through a length of fiber, if I hit it at the right wavelength, the loss can be quite low, but still there is going to be some loss, maybe 0.2 dB kilometer or 0.15 dB per kilometer or something like that, if I'm at the sweet spot at the wavelength. But if you have a given length of fiber, of course, you're only storing for however long it takes the photon to get through that length. So it's not particularly easy to configure that or reconfigure that. In principle, you could hook up fibers with some sort of a switch, an integrated optics switch. And the difficulty there is that the insertion loss in those switches tends to be pretty high. And if you go back and look at one of these earlier talks, we see that we need to have efficiencies really quite high for the whole scheme, better than, let's say, 70%, something like that. And so high insertion loss on an integrated optics switch tends to be death for this sort of a solution to that. Okay, so instead, we're going to do what my colleague Elizabeth Goldschmidt has called the world's best but the world's stupidest quantum memory, just based on the fact that if I just allow photons to propagate in free space, it takes them 1 nanosecond to go 1 foot. And so if I want to store 10 nanoseconds, I'll make them go 10 feet. Or if I want to store a much longer time, 26.6 microseconds, for example, I could take the LIGO mirrors and go out to the end stations and come back. So that is actually not what will I say? Not a practical way, I guess I'll say, of being able to do storage, because we don't want to have to set up LIGO length vacuum chambers, at all the different nodes in our architecture. But nevertheless, you can get good performance because it's possible to get mirrors with extremely high reflectivity. Okay, so this then brings us to this loop quantum memory kind of shown here, where, for example, we have a horizontally polarized photon coming in, and it will be transmitted by this polarizing beam splitter. If I don't do anything to it, it will just go straight through. If I use a device to rotate the polarization to vertical, this is one way of doing this is called a Pockle cell, where I put, in this case, let's say a couple thousand volts on this device, and that will rotate the polarization from horizontal to vertical. And that vertically polarized photon will then cycle around in the system. I'm presuming that you guys, yeah, okay. You can see my mouse because I can see it on my other computer. Great. So it can be stored in the system until we switch the polarization back to horizontal, and then it will leave. So a relatively simple idea, I guess you would agree. And we can get pretty good, time resolution in this case of, of order 10 nanoseconds, something like that. It takes of order a couple nanoseconds to fire the Pockle cell, so we wouldn't go too much shorter than that with this scheme. Okay, the mirrors on this could be quite good, but the transmission of the Pockle cell and the polarizing beam splitters is also quite good, but not super good. So it's maybe only 99%. So let's say we had a scenario where I wanted to store for 537 cycles of this. That's not going to work well because the net transmission is going to be passing through this lossy, switchy items, 537 times, and basically nothing is going to come out the other end. So one strategy that we can use to sort of improve that is to do a stacking where we have memories of different lengths. Let's say in this case, I'm showing it as a digital arrangement where each one is 10 times longer than the previous one. So if I wanted to now store for 537 of this base time, instead of going 537 cycles through the shortest system, I'll go 7 cycles through the short system, 3 cycles through the medium length, and 5 cycles through the longest one. And in that case, again, assuming that the mirror reflectivities have 4 nines reflectivity, so 99.99, and again, assuming that we have this 99% transmission through the Pockle cell polarizing beam splitters, now the net loss in this case, because I'm only going through the lossy elements, which are the Pockle cell and the polarizing beam splitters, I'm only going through them 7 plus 3 plus 5 times instead of 537 times. So now I end up with a net transmission of 70%, something like that. So that is going to be obviously much, much, much more efficient. I'm showing this as a digital scheme and up to a factor of let's say 999 cycles. I think for ASPEN Net, we don't need that, but we might need to do something where we have 2 stages and maybe one of them is 6 times longer than the other one. So counting in a slightly different way, and that will be the most efficient scheme. You can do the optimization once you know what the loss in all the elements, then you can figure out, and depending on how many cycles you want to incorporate, what's the optimal strategy. I will just say one more thing. The optimal, if you have unlimited funds, is just go up by a factor of 2 each time, just count up in binary. Then you can go up to 1,024 cycles by going through these switches exactly 10 times. That will be the minimum then. And that 2 to the 10 is 1,000, is over 1,000. But the only reason you wouldn't want to do that is that these switches are not super cheap. And so maybe you don't want to have 10 of them in the system. Okay, going through these longer times, if you want to go through a middle time, you can use spherical mirrors, and that allows you to get an elliptical pattern. This is called a Harriet cell, where you come in through one hole in the mirror, bounce back and forth between the mirrors, let's say 40 times, and then leave through the hole in the other mirror. If you want to go even longer than that, let's say the one thing that's 1,000 nanoseconds in a relative, with mirrors that are only separated by a meter, then we need something that's more complicated. So there's this other arrangement where you have a spherical mirror and 2 flat mirrors, which are slightly angled with respect to each other, slightly tilted. And we get this sort of complicated Lissajous-esque pattern where the light comes in over the top of one mirror and then leaves right near the bottom of the other mirror. Okay, and if we have, again, 4 nines reflectivity on this, and we're bouncing off the mirrors 340 times, then that corresponds to something like a 97% transmission. Turns out you can send different spatial modes into this, so you can angle the input beam and store, let's say, in this case, 8 separate different spatial modes can be stored simultaneous. Also, if you make slight adjustments to the cell, then you can have a controllable, tunable delay just by sort of changing what the pattern is. Allows you to, well, anyways, controllably tune exactly what the delay needs to be.
Paul,
Okay. Yes, please.
Alan Migdal had a question. Alan, do you just want to unmute yourself?
You can read it.
Sure. Your factor of 10 caught my attention. And my question is that really the optimum, or would it be?
No. Like that's what I was saying. Doing things in binary would be best. When we had
Okay.
the factor of 10, if I wanted to go up to 999 cycles, I might have to go 9 times and 9 times and 9 times, so 27 times through my switches.
Yeah.
If I do it in binary, if I had 10 binary steps, then I'd only have to go through
Okay.
10 switching cycles. So that's better. It's just that it's more expensive.
Okay. Cool.
So, Paul, I've got a question on the Roberts cell.
Great.
Right here, when you're showing this continuous adjustment, is it really a continuous adjustment of the time? So
This is
like,
in this. Yeah, this is changing the separation between the mirrors and also one of the tilt angles at the same time.
okay, so it is continuous. How much do you have in timing? You know, how much can you tune it easily?
I don't know what easily means. I mean,
Well, just say, yeah, maybe the angle or
you're
something
pulling
like
back
that.
one of the mirrors, you're having to keep the relative angles kind of at a precise angle. So the question is, does that actually occur?
Okay.
You have to have some arrangement where when you pull it, you don't have any kind of tilt associated with it.
Okay.
That is what I will definitely say is just an engineering problem, but it's not one that I claim that we've looked at in any detail. So I'm not really prepared to say exactly how much.
Okay, I got
You
it.
can
All
also,
right,
if you
thanks.
change the spot pattern where you have one less bounce, then of course you can, or half the number of bounces, then you can of course make much larger changes to how long things are stored.
Right. No,
So you
that
don't have to
I
have
guess I get that.
430, or you don't have to have 430 bounces. You could have 215 or 100, and anyway,
Sure.
there's a whole range of solutions.
Sure. Okay, great. Thank you.
Sure. Okay, so this is just some measurements that we've made on our system where we're at these different loops of different lengths and showing what the end-to-end efficiency is. This is coupling into single mode fiber at the end, and kind of what the fitting the drop off to what the overall efficiency is. And then showing if we kind of couple everything together where this is storing anywhere from 1 cycle all the way to 999 cycles with this kind of a concatenated scheme. It's not clear, again, for the ASPEN net that we need that kind of concatenated scheme. It might, in fact, be enough to just do a single loop for what we need to do. So it is possible to store sort of dual rail encoded qubits in these, say polarization qubits or time bin qubits. The way we would do polarization qubits, which again is not what ASPEN Net is proposing to do, but just because this has maybe wider applicability, you can convert the polarization qubit into a time bin qubit using a transducer like this, where one polarization component goes a short path, one goes a long path. They end up then separated in time, and then I'll use, again, a Pockle cell to rotate the later one so that it also has horizontal polarization. And then we send this time bin encoded qubit into the memory. And then when it comes back out, we just go back through the same system, kind of a cheap animation, just taking the same thing and reversing it. Anyway, you go back through the same system and it sort of stitches everything back together again. And then you're back to a polarization encoded qubit. So we've done that and been able to show that we can maintain very high fidelities of the different loops, you know, in the 99% level for preserving qubit states. And we think we should be also able to store spatial mode qubits and certainly also some different frequency qubits. So let me talk about that last in just a little in the context of the bandwidth of all of this, because I started this whole thing saying we'd really like to be able to store for, you know, tens, 10 terahertz or something like that. And the thing is, for this type of memory, we're only limited by the bandwidth of the mirrors. And so, for example, sorry, by two things, the bandwidth of the mirrors and the Pockle cell switching. So these mirrors are better than 99%, sorry, 99.99% over, as you see, 40 nanometers of bandwidth. And okay, the other thing that's limiting us is that my Pockle cell is supposed to be putting, let's say, 180-degree phase shift on one component of polarization. And if you change the wavelength by 10%, you'll change that phase shift, roughly speaking, by 10%. So then it won't be switching as accurately. So this is the effect on the Pockle cell switching probability. But nevertheless, we see that we can still get an efficiency that's really very, very high over let's say 10 terahertz. Also, you can get these mirrors so that they can have dual wavelength coding, so they can work, for example, at 800 nanometers and at 1500 nanometers or some other combination. So in terms of comparing them with fiber, really quite a bit better because we're not limited to just working at 1550. There's not any dispersion to speak of, at least that we've been able to observe in the types of systems we've been putting in. They don't tend to change the polarization, unlike fiber. So it certainly seems to have quite a few advantages. This is just doing one of these other plots that I showed before, where we are in terms of time and bandwidth. And so it seems to have some advantages. Again, as long as we don't need to store for more than, say, 10 microseconds or something like that. Let's see. Let me ask if there are questions at that stage. I mean, I certainly have other things to talk about, but this is, you kind of get the central idea of what the scheme is.
I guess you mentioned on the dispersion. I mean, if you sent in a pulse with 10 terahertz bandwidth, the mirrors aren't going to introduce, or the Pockle cell?
Yeah, okay, they will. Yes, that's true. They over that larger bandwidth, there will be some minor dispersion. I guess I'm thinking in terms of like down conversion sorts of pulses. If we're trying to send in, I got to 10 terahertz by doing a factor of 100 spectral multiplexing.
Yeah.
But each of the spectral channels only needs to be, let's say, 10 gigahertz. And so the dispersion that you get over 10 gigahertz is actually very small.
Sure. Okay. Okay.
But it is true that over the entire bandwidth, you'd find that channel number 57 was getting a slightly different dispersion than some other channel. Again, I don't think that's actually a problem, because you're going to treat the individual spectral channels differently anyway, and you can fix that fact. Okay, so this is just to show that we basically use this in.
Sorry, Rob, do you have a question? I think Rob
Maybe just a quick one. Well, it always is a quick one, and then it's going to be a long answer. I was just curious why it seems like you have the long delay at the end and the short delay at the start. If I'm thinking about if I need to sort of make a feed forward, that's going to take some time. So I'd maybe want the long loop first while I think about how long I need to wait.
Yeah, you could do this. So as we've been envisioning this initially, when you send the photon in, how long you're trying to store it for. So the feed forward's kind of already happened in that scheme. But you're absolutely correct. You might not know that, and you might want to go into the long one first. It really kind of depends. The thing is, once you're in the long one, you don't get out until you're out of it after one cycle. So you're kind of stuck. Whereas if instead the information's coming in, if you go through the short ones first, it turns out you don't need to go through the long one. You just never need to go through the long one. Whereas if you go to the long one first, you are kind of stuck in that regard.
Okay. I think I was sort of was related to the way I was thinking about these. Normally, you have the memory on the link that's going to the Bell state measurement, the swapping, and not the local state. And I wasn't sure what was the choice there, why you did it that way around.
Yeah, so let's just say that there are different trade-offs depending on where it is, and we could have a side discussion about what the optimal is. And I'm not willing to get up and fight more than 51% to say that what I put was the optimal. It really depends a lot on what all the losses are, what all the rates are. I think you have to look at the whole system to figure out where the optimal place to put things is.
Okay, thanks.
Okay, so in this kind of simple demonstration that we did several years ago. This is my postdoc Fumihiro at the time. The idea was to do a measurement device independent enhanced synchronization enhanced protocol. And it's kind of just shown here that we're sending a single photon. It was a heralded single photon. We can change what the quantum state encoding was, and then we're going to do a Bell state measurement on that and another photon coming from the other side. Again, because of the fact that a lot of the pulses are not occupied, because we're driving this non-deterministic source. It's pulse, but it's not deterministic. If we can get a heralding signal, then we can tell the person in the middle which of the two photons should be delayed so that it matches the other one. In particular, obviously, you'll delay the one that comes in first so that it matches the one that comes in later. So this is a so-called relative temporal multiplexing. Someone else introduced that name. I can't quite remember who introduced it. We were doing it before we saw the name, but it's a good name anyway. Okay, so in this case, we're going to make the memory length match the pulse spacing. In this experiment, that was 10 nanoseconds. And then again, we'll let the photons come in. And in fact, we sort of had it set up so that we could use a single memory, and we could either, with circulators, either input from the left side going clockwise or from the right side going counterclockwise, and then the photons would still come out. And so in that way, and by having them come in at slightly different times, offset half a cycle, you could be sure that you would only switch one of them and not, or only delay one of them and not the other one. Okay, and then do some combination in the middle. In this particular protocol, we need to do a Hongo-Mandel, so there were two photons coming in. In the ASPEN Net architecture, there'd only be one photon coming in, but we'd still be combining those two modes on a beam splitter, so similar to what was done here. Okay, so you've kind of seen the relevant part in the center. That's kind of all I wanted to focus on. And just to show that by doing this kind of multiplexing, we're able to see in this experiment actually up to a factor of 30 enhancement in the overall rates, just because of the fact that we're able to combine photons that don't have to arrive in the same bin. They can arrive anywhere in any of 30, well, in this case, anywhere up to 40 time bins, and yet they get mapped onto the same time bin at the end. So that's the huge advantage of this sort of synchronization, and you absolutely need that in order for the ASPEN Net protocol to, I think, to be functional. Okay, and then we also showed that the memories did not affect the Hongo-Mandel interference. You can't really tell in this case that they didn't affect it, but this is a comparison. This is showing what we got after the memory, and it was the same as what we had before the memory. So the memory itself wasn't making things any worse. Okay, and then just the last thing in 1 minute, people have asked, well, how long could we actually store for? And so we've been looking at some other folded geometries where we actually have a lot more bounces, and we could just do a calculation comparing, for example, memories that had 5 nines reflectivity, for example, to going through fiber. And this is for however long you're trying to store, this is going through fiber. And then all of the other colored things up here, this is going through the free space memory. There's a bunch of different colors because if you have gas and water vapor in the memory, then you'll get scattering from those. But if you pump it out, you end up only getting a loss of a few percent, 4%, even going out to say 50 microseconds. And so you end up doing quite a bit better than fiber, which is at 70%, up at 96% by going through free space. And in fact, there are mirrors supposedly that can even have 6 nines of reflectivity. And if you were to just blindly put in those numbers, not assuming anything about what's going on with modes or assuming they're all perfect, but just putting in those numbers, in principle, you could actually store for 10 milliseconds using this kind of a free space system. Whereas, of course, fiber, you absolutely wouldn't be able to do that. Okay, so I just want to acknowledge Nathan Arnold, who is the graduate student who is doing all the quantum memory stuff, or at least a lot of it in my group. And we're, of course, always looking to talk to other people. But that is what I had.
All right, thanks a lot, Paul. Anybody have any questions? Just either put them in the chat or feel free to unmute yourself. Okay, so since we're at the top of the hour, and in the interest of time, and since people ask questions already, I think we will end today's session there. I just want to remind folks that our next session will be in 2 weeks, and it's actually going to be a talk on photon sources and how to actually do quantum compatible phase stabilization of fiber. And so I'll be giving the photon sources tutorial. It'll be 30 minutes. And Nick Nardelli, who is a coworker of mine here at NIST and colleague, will be talking about the phase stabilization. And because it was asked for, I'm also going to just try to throw in a few minutes about like some of our measurements and how we're actually proposing to do some of these displaced vacuum measurements. Because I think Rob and a few other folks asked about that during like Zurich talk last time. So, and one last announcement, our website, quantum-aspen.net, now has the recordings of these tutorials as well. You can go to the tutorials tab and you can find the recordings of the past tutorials, and we'll try to make today's tutorial available in the next day or so as well. So thanks everyone, and we'll see you hopefully in 2 weeks.
And hopefully also at the ASPEN Net Town Hall at the Quantum 2.0 meeting.
Oh yes, good plug. So thanks.